Think about the worst moment of your life. Not a bad day, not an embarrassing memory. The worst moment. The one you would give almost anything to go back to and change. You know the one. Now here is the thing that physics wants you to understand about that moment. Not the comforting version, not the philosophical version about acceptance and growth, the physical version. That moment is still happening. Not metaphorically, not in your memory. In the structure of space-time itself, that moment, that exact configuration of matter and energy and position exists as a fixed coordinate in four-dimensional reality. The past is not gone. It is not erased. It is geometrically present in the fabric of the universe, as real and as permanent as the chair you are sitting in right now. You cannot go back to it. Not because of a lack of technology, not because we haven't built the right machine yet, but because of something far more fundamental. Something written into the structure of reality at a level so deep that it shows up in every physical law we have ever discovered. Time moves in one direction. And despite everything physics tells us about the symmetry of the universe, despite the fact that almost every fundamental law of physics works equally well run forward or backward, despite the fact that at the level of individual particles there is essentially no preferred direction of time, despite all of that, the universe moves inexorably from past to future, and nothing in it has ever been observed to move the other way. This is called the arrow of time, and it is one of the deepest unsolved problems in all of physics. In this video, we are going to go through exactly what the arrow of time is, why it exists, and what the best physics we have says about whether going back is truly impossible or just extremely, cosmically, thermodynamically unlikely. There is something in the second half of this video that most people find more disturbing than the impossibility of time travel itself. It is the implication. What the arrow of time tells us about the nature of the universe we live in, about whether the past is real, whether the future is determined, and whether the present moment you are experiencing right now is special in any physical sense. It is not what you expect, and it will change the way you think about every second that passes. Stay with me. Before we go further, think about this. If you could go back to one moment in your life and change it, what would happen to the version of you that made the original choice? Drop the moment below. We will come back to why that question has a physical answer that most people find deeply uncomfortable. Let's start with the thing that makes the arrow of time scientifically strange. Pick any fundamental physical process. A collision between two billiard balls, an electron emitting a photon, two particles interacting via the electromagnetic force, the gravitational attraction between two masses. Now film that process. Play the film backward. In almost every case, in virtually every fundamental physical process we know of, the reversed film is also a valid physical process. It obeys all the same laws. There is nothing in the mathematics of the interaction that distinguishes the forward version from the backward version. This is called time reversal symmetry, and it holds for almost all of the fundamental laws of physics. Newton's laws of motion are time symmetric. If you reverse time, objects that were decelerating start accelerating, and objects that were moving apart start moving together. And the entire system evolves perfectly consistently with Newton's laws in reverse. Maxwell's equations of electromagnetism are time symmetric. The equations that describe how electric and magnetic fields propagate work equally well in both time directions. A film of an electromagnetic wave propagating through space, played backward, is still a valid electromagnetic wave. Quantum mechanics is almost entirely time symmetric. The Schrödinger equation, the fundamental equation describing how quantum states evolve, is time symmetric. Run it backward, and you get a perfectly valid quantum evolution. Even Einstein's general relativity is time-symmetric at the level of the field equations. The mathematics describing how mass curves spacetime and how spacetime curves the motion of mass does not distinguish between past and future. So here is the problem. If the fundamental laws of physics are time-symmetric, if every individual process at the microscopic level works equally well forward and backward, then where does the arrow of time come from? Why does everything at the macroscopic level, everything you can see, touch, and experience, move so clearly and so irreversibly from past to future? Why does a broken egg never spontaneously reassemble? Why does heat flow from hot objects to cold ones and never spontaneously reverse? Why do you remember the past and not the future? Why does the universe age? These questions are not rhetorical. They are among the most fundamental open questions in physics. And the answer, or rather, the best answer we currently have, is both more satisfying and more disturbing than most people expect. The T-violation in particle physics is real. It is measured. It tells us that time is not perfectly symmetric even at the fundamental level. But the effect is so small, appearing only in the decay of certain exotic particles under very specific conditions, that it cannot account for the overwhelming, universal, thermodynamic arrow of time that governs everything you experience. The arrow of time you experience every moment of your life is not primarily about particle physics T-violation. It is about something else entirely. It is about entropy. You have heard of entropy. You probably know it has something to do with disorder. You may have heard the phrase, entropy always increases. What you may not know is what that actually means, and why it is the most important fact about your existence. Entropy, in the thermodynamic sense, is a measure of the number of microscopic configurations that correspond to a given macroscopic state. It is a measure of how many ways a system can be arranged at the microscopic level while still looking the same at the macroscopic level. Consider a room with air molecules. The air in the room could be distributed in an enormous number of microscopic configurations, different positions and velocities for each of the approximately 10 to the 27th molecules in the room, while still appearing at the macroscopic level as a room uniformly filled with air at a certain temperature and pressure. Now imagine all the air in the room spontaneously rushing to one corner, leaving the rest of the room in vacuum. This is a macroscopic state with far fewer microscopic configurations. The molecules all have to be in that one corner rather than distributed throughout the room. It has lower entropy. The reason this never happens spontaneously is statistical, not fundamental. There is no law of physics that forbids all the air molecules from rushing to one corner. At the level of individual molecular collisions, all of which are time-symmetric, there is nothing preventing it. What prevents it is probability. The number of microscopic configurations in which the air is uniformly distributed is so vastly larger than the number of configurations in which it is all in one corner that the probability of the latter occurring spontaneously is not zero. It is just so close to zero that the expected waiting time for it to occur exceeds the age of the universe by a factor that has more zeros than atoms in the observable universe. The second law of thermodynamics, entropy always increases in a closed system, is not a fundamental law in the sense that Newton's laws or Maxwell's equations are fundamental laws. It is a statistical statement. It says that systems spontaneously evolve toward higher entropy states because there are overwhelmingly more high entropy states than low entropy states, and random evolution through state space will almost always move toward more probable configurations. This is why heat flows from hot to cold. A hot object has its energy concentrated in a small number of highly energetic molecules, a relatively low entropy configuration. A cold object has its energy distributed more evenly. When they are in contact, energy transfer from hot to cold increases the total entropy of the system. It moves the system toward more probable configurations. This is why broken eggs do not spontaneously reassemble. The assembled egg is an extremely specific, low entropy configuration. The broken egg is one of an astronomically larger number of configurations. Spontaneous reassembly would require the system to move from high entropy to low entropy, from a more probable state to a less probable one, which is not forbidden, but is so statistically unlikely as to be, for all practical purposes, impossible. And this is the arrow of time. Time appears to move in one direction, from past to future, because entropy increases in that direction. The past is the direction of lower entropy. The future is the direction of higher entropy. The arrow of time is the direction of increasing entropy. Boltzmann's equation is carved on his tombstone. That detail is not incidental. Boltzmann spent much of his career defending the statistical interpretation of entropy against critics who argued that the irreversibility of thermodynamic processes required a more fundamental explanation. He was largely vindicated after his death. But Boltzmann's statistical explanation of entropy raises an immediate and profound question. If entropy increases because high entropy states are more probable than low entropy states, if the arrow of time is a consequence of statistical mechanics rather than fundamental law, then why was entropy ever low? The second law says entropy increases. It implies that entropy was lower in the past than in the present, and lower still before that. Going backward in time, entropy decreases, all the way back to the Big Bang. The universe began in an extraordinarily low entropy state. This is not a conclusion, it is an observation. We can measure the entropy of the early universe from the cosmic microwave background, the afterglow of the Big Bang. The early universe was in a state of almost perfect thermal equilibrium, which sounds like high entropy, but is actually extremely low entropy when you account for gravity. A universe of matter and energy in thermal equilibrium, without the gravitational clumping that produces stars, galaxies, and black holes, is in a far lower entropy state than a universe with the complex gravitational structures we observe today. The arrow of time, the reason you remember the past and not the future, the reason eggs break and do not reassemble, the reason you are aging, traces back to a single fact. The universe began in a very low entropy state. This is called the past hypothesis. It was named by the philosopher David Albert. And it is the deepest explanation we currently have for the arrow of time. The arrow of time is not a fundamental feature of physical law. It is a consequence of the initial conditions of the universe. The universe happened to start in a very specific, very improbable, very low entropy configuration. Everything that has happened since, every physical process, every chemical reaction, every thought you have ever had, is the universe moving from that improbable initial state toward more probable configurations. You experience time moving forward because you are the universe evolving away from its initial conditions. Now we come to the part that most people find the most disturbing. Not the physics, the implication. If the arrow of time is a consequence of entropy, if the direction of time is the direction of increasing disorder, then what does that say about the past, about the future, about the present moment you are experiencing right now? Let's start with the past. In 1905, Albert Einstein published his special theory of relativity. Among its consequences was a result that completely transformed the concept of time. There is no universal present moment. In Newtonian physics, the physics of everyday intuition, time is absolute. There is a universal now. Every event in the universe happens at a specific moment on a universal clock. The past is the set of all events that have already happened. The future is the set of all events that have not yet happened. The present is the razor-thin boundary between them. Special relativity destroyed this picture. In relativity, simultaneity is relative. Two events that are simultaneous for one observer are not simultaneous for an observer moving relative to the first. The order of events depends on the observer's reference frame. Two observers moving relative to each other will disagree about which of two spatially separated events happened first. This is not a philosophical claim. It is a measurable, physical fact, confirmed by every experiment that has tested it. The implication is that the concept of now, of a universal present moment, does not exist in physics. There is no moment in time that is privileged as the present in any observer-independent sense. What replaces it is the block universe, a view of reality in which all of spacetime, past, present, and future, exists simultaneously as a four-dimensional structure. In the block universe, the past is not gone. The future is not yet to come. Past, present, and future all exist equally as different regions of the same four-dimensional spacetime. Your past, every moment of your life that has already happened, exists in this picture as a fixed, unchangeable region of spacetime. The worst moment of your life exists as permanently and as really as the chair you are sitting in. Your future, every moment of your life that has not yet happened, also exists in this picture, already determined by the structure of spacetime. The present moment, the moment you are experiencing right now, reading these words, is not special in any physical sense. It is simply the region of spacetime your consciousness happens to be processing at this particular point in your world line. The block universe is not a fringe idea. It is the view of spacetime that emerges most naturally from special relativity, and it is taken seriously by a significant fraction of physicists and philosophers of physics. If the block universe is correct, then you cannot go back to the past, not because the past has been erased, but because your position in spacetime is a fixed trajectory through a four-dimensional structure that you cannot leave. You move along your world line from birth to death. The rest of spacetime, including every moment of your past, exists around you, geometrically present, permanently inaccessible. The block universe has a consequence for free will that is worth sitting with. If the future already exists, if your entire life trajectory is a fixed world line through four-dimensional spacetime, then the choices you make are not creating new futures. They are features of a spacetime structure that already exists in its entirety. Your sense of deliberation, of weighing options, of genuinely choosing between alternatives, in the block universe, this sense is real as an experience, but the outcome of the deliberation is already part of the spacetime structure. This is not determinism in the Newtonian sense, the sense in which the future is determined by the precise positions and momenta of every particle, in principle calculable if you had perfect information. It is something stranger. The future is not merely determined. In the block universe, it exists. It is already there geometrically in the four-dimensional structure of spacetime. You have not made the choices you will make next year. But in the block universe, those choices already exist as coordinates in spacetime. This is the implication that most people find most disturbing. Not the arrow of time, not entropy, not the impossibility of going back. The possibility that the future is not something you are creating, it is something you are discovering. Stop here for a second. If the block universe is correct, if your future already exists as a fixed structure in spacetime, does that change anything about how you make decisions? Does it matter? Comment below. There is no correct answer, but there is a physical one, and it is in the next section. Now let's talk about what physics actually says about time travel. Not the Hollywood version, the physics version. And the physics version is more complicated than a simple yes or no. There are two types of time travel that are worth distinguishing: travel to the future and travel to the past. Physics treats them very differently. Travel to the future is not only possible, you are doing it right now at a rate of 1 second per second. But you can do better than that. Special relativity predicts that time passes more slowly for a moving observer than for a stationary one. This is called time dilation. It is not a theoretical prediction that is yet to be confirmed. It is a measured fact, confirmed by every precision experiment that has tested it. GPS satellites orbit Earth at approximately 14,000 kilometers per hour. At that speed, special relativistic time dilation causes their clocks to run slightly slow relative to clocks on the ground, losing approximately 7 microseconds per day. General relativistic effects, the weaker gravity at altitude, cause their clocks to run slightly fast, gaining approximately 45 microseconds per day. The net effect is a gain of approximately 38 microseconds per day. 38 microseconds does not sound significant, but GPS systems require timing accuracy to within approximately 20 to 30 nanoseconds to provide meter-level positioning accuracy. Without corrections for both special and general relativistic time dilation, GPS systems would accumulate positioning errors of approximately 10 kilometers per day. The corrections are applied continuously. GPS works because we account for relativistic time. Time dilation at the speeds available to current technology is small, but it scales. At 90% of the speed of light, time passes approximately 2.3 times more slowly for the moving observer. At 99% of the speed of light, time passes approximately 7 times more slowly. At 99.9%, approximately 22 times more slowly. A particle accelerator can accelerate muons, unstable particles with a half-life of approximately 2.2 microseconds, to 99.94% of the speed of light. At that speed, relativistic time dilation extends their observable half-life to approximately 64 microseconds. We measure this directly. The muons survive longer because, from our perspective, time is passing more slowly for them. In principle, a human being traveling at a sufficiently high fraction of the speed of light could travel for what felt to them like a few years while thousands of years passed on Earth. They would return to a future Earth. They would have traveled to the future, irreversibly, with no way back. This is time travel to the future. It is physically permitted. It requires enormous energy. It is a one-way trip, but it is real. Travel to the past is a different matter entirely. To travel to the past, to return to a moment that is, in the block universe, already fixed in spacetime, physics requires something called a closed time-like curve. A closed time-like curve is a path through spacetime that returns to its starting point in both space and time. A world line that loops back to where and when it began. Following such a path, an observer would return to a moment in their own past. Do closed time-like curves exist? Can they exist? General relativity, Einstein's theory of gravity, permits them in certain solutions to the field equations. The first person to point this out was not a science fiction writer. It was Kurt Gödel, the same Kurt Gödel who proved the incompleteness theorems that shook the foundations of mathematics. In 1949, Gödel presented Einstein with a solution to the general relativistic field equations describing a rotating universe. In Gödel's universe, closed time-like curves exist everywhere. Any observer can, in principle, follow a path through spacetime that returns them to any point in their own past. Einstein was deeply troubled by Gödel's solution. Not because it was mathematically incorrect, it was not, but because of what it implied. If general relativity permits a universe in which time travel to the past is possible, what does that say about the nature of time, about causality, about the structure of reality? Einstein never found a satisfactory response to Gödel's solution within the framework of general relativity. Gödel's universe is not our universe. Our universe does not appear to be rotating in the way Gödel's solution requires. But other solutions to the general relativistic field equations also contain closed time-like curves. The Kerr solution, the solution describing a rotating black hole, contains closed time-like curves in the region inside the inner event horizon. The mathematics permits them. Whether they are physically accessible, whether an observer could actually traverse them, is a separate question. Roy Kerr discovered this solution in 1963. The theoretical possibility of time travel via rotating black holes has been in the physics literature for over 60 years. Wormholes, hypothetical connections between distant regions of spacetime, also potentially permit time travel to the past. If one mouth of a wormhole is accelerated to relativistic speeds and then returned to its original position, time dilation would cause the two mouths to be offset in time. An observer entering one mouth could emerge from the other at an earlier time. In 1988, Kip Thorne, who would later win the Nobel Prize in Physics for the detection of gravitational waves, and his colleagues published a paper in Physical Review Letters examining the physics of traversable wormholes and their potential use for time travel. The paper concluded that traversable wormholes are not obviously forbidden by known physics, but that the matter required to keep them open, exotic matter with negative energy density, has not been confirmed to exist in the required quantities. Thorne's paper was not a proposal for how to build a time machine. It was an analysis of what physics does and does not forbid. The conclusion was nuanced. Traversable wormholes and the time travel they might permit are not ruled out by general relativity. Whether they are ruled out by a complete theory of quantum gravity, which we do not yet have, is unknown. This is where the answer to the question of time travel currently stands. Not a definitive no, a conditional no that depends on physics we do not yet have. Let's assume, for the moment, that time travel to the past is physically possible, that closed time-like curves exist and are traversable, that you could, in principle, follow a path through space-time that returns you to a moment in your own past. What happens then? This is where the paradoxes enter, and they are not just philosophical puzzles. They are physical constraints that any theory of time travel must address. The most famous is the grandfather paradox. You travel back in time, and through some chain of events, prevent your own grandparents from meeting. You are therefore never born. You therefore never travel back in time. You therefore do not prevent your grandparents from meeting. You are therefore born. You therefore travel back in time. You therefore prevent your grandparents from meeting. The loop is logically inconsistent. It cannot be resolved within standard causal logic. There are three possible responses to the grandfather paradox in physics. The first is that closed time-like curves are physically impossible, that something in the laws of physics, perhaps a complete theory of quantum gravity, forbids their existence. This is Hawking's chronology protection conjecture, proposed in 1992. Hawking argued that the laws of physics conspire to prevent the formation of closed time-like curves, thereby protecting causality. He did not prove this conjecture. It remains unproven. The second response is the Novikov self-consistency principle. Proposed by physicist Igor Novikov, it states that any events occurring on a closed time-like curve must be self-consistent. They must not create logical contradictions. Under this principle, if you travel to the past, everything you do there must be consistent with what actually happened. You cannot change the past. You can only participate in it in ways that were always part of what happened. In the grandfather paradox, the Novikov principle says the following. You will find that you cannot kill your grandfather, even if you try. Not because of any external force preventing you, but because the universe's causal structure makes it impossible for events to unfold in a way that creates a contradiction. Something will always intervene. The gun will jam. You will miss. You will have a change of heart. The past is not changeable. It is fixed. And any time traveler who visits it is already part of its fixed structure. This is a profound and deeply strange picture of reality. The past is not something you can alter. It is something you can join. Any time traveler who goes back has always been part of the historical record of that period. The causal structure of spacetime ensures consistency. The third response is the many worlds interpretation. The possibility that time travel to the past creates a branch in the wave function of the universe. You travel back, you change something, and the result is not a paradox, but a new branch of reality, a parallel universe in which the change you made is part of the history. The original universe continues unchanged. You are now in a different branch. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, is a legitimate and seriously held position in the foundations of quantum mechanics. It does not require time travel to motivate it, but it provides a potential resolution to time travel paradoxes. Which of these three possibilities is correct? Chronology protection, Novikov self-consistency, or many worlds branching cannot be determined with current physics. All three are internally consistent. All three have implications that extend far beyond the specific question of time travel. Hawking's empirical argument is worth dwelling on. He noted, partly humorously, that we have no evidence of visitors from the future. No time tourists have appeared to witness historical events. No messages have arrived from our descendants. If time travel to the past were possible and eventually developed by some future civilization, we might expect some evidence of it. We have none. This is not conclusive. Perhaps time travel, even if possible, can only go back to the point in time when the first time machine was created, so no time traveler could visit an era before time travel was invented. Perhaps time travelers exist, but are careful not to be detected. Perhaps time travel is possible, but is never developed by any civilization. Or perhaps Hawking was right, and chronology protection is real, and the laws of physics that we will eventually discover, the complete theory of quantum gravity, will contain, somewhere in their structure, a prohibition on closed time-like curves. We do not know. What we do know is this: the moment you experienced 5 minutes ago is gone in a thermodynamic sense. The entropy has increased, the information has dispersed, the specific configuration of matter and energy that constituted that moment has evolved into the current moment and cannot be reconstructed. The past exists in the block universe as a geometric fact, but it is thermodynamically inaccessible. The entropy gradient is absolute in practice, even if not in principle. The worst moment of your life exists as a fixed coordinate in four-dimensional spacetime. You cannot go back to it. Not because physics definitively forbids it, but because the thermodynamic arrow of time, the practical implications of entropy, and the possible chronology protection of quantum gravity together create a barrier that is, for all purposes available to any being in this universe, absolute. The past is real. The past is permanent. The past is inaccessible. And the present moment you are experiencing right now, this exact second, is already becoming part of that permanent, inaccessible past. Let's bring this back to where we started. Think about the worst moment of your life. In the block universe, that moment exists. It is a fixed, permanent, geometrically real feature of the four-dimensional space-time structure you inhabit. It is as real as the present moment. More real, in a sense, it is more firmly established, more causally fixed, more certain in its existence than the future. You cannot go back to it. The entropy that has accumulated since then, the dispersal of information, the increase in disorder, the evolution of the universe's causal structure away from that moment, represents a barrier that nothing in known physics can overcome. But here's the thing that the physics of time actually offers, which is stranger and in some ways more useful than the fantasy of going back. The present moment, this moment, right now, is the only region of space-time where anything can be changed. The past is fixed. The future, if the block universe is correct, may already be fixed. But the future is not yet past. It is not yet thermodynamically established. it is not yet causally frozen. The arrow of time points forward. Entropy increases forward. The universe is building its causal structure forward, one moment at a time, from the extraordinarily low entropy initial state of the Big Bang toward the high entropy equilibrium of the distant future. You are part of that process. Your choices, whatever their ultimate ontological status in the block universe, are the mechanism by which the causal structure of spacetime at your location evolves forward. The future region of spacetime that you will inhabit has not yet achieved the thermodynamic irreversibility of the past. It is still, in the only sense that physics permits, open. The worst moment of your life is real and permanent and unreachable. The present moment is the only place where the future gets written. That is what the arrow of time actually tells you. Not that the past was not real, not that it was a dream, not that it did not matter, that it is over. Completely and permanently and physically over. And that the only direction physics permits you to move is forward. The arrow of time is not a fundamental law. It is a consequence of where the universe started. The impossibility of going back is not absolute. It is thermodynamic, statistical, and possibly, if Hawking's chronology protection conjecture is correct, ultimately enforced by quantum gravity. The past is real. The future may already exist. The present is the only region of spacetime where entropy has not yet frozen the causal structure into irreversibility. And time travel to the future, real, physical, confirmed time travel, is happening right now. You are doing it, 1 second at a time. The question is whether you are moving through it or it is moving through you. Physics does not have a final answer to that, but it has something more valuable than an answer. It has the question. Precisely formulated, mathematically stated, open. And open questions, in physics, are where the next 100 years of understanding get built. One question before you go. If you knew, with certainty, that the block universe is correct and your future already exists as a fixed structure in spacetime, would you still make plans? Would you still feel like your choices matter? One word or one paragraph, I want to know. And I will respond to the most interesting answer in the next video. Next video, what happens to Earth's magnetic poles when they flip? And why the last time they did, something in the fossil record changed in a way that scientists are still trying to explain. The flip is not coming. According to current measurements, it has already started. See you there.